continue to tell you about this kind of picture which appears right now on the screen, and that is to say, which is a picture of a passive scalar in a turbulent flow, and in particular, a passive scalar which is here in a fully turbulent state. So it's the continuation of the discussion that we had started yesterday. Passive scalar turbulence. And just to remind you of the conclusions that we reached yesterday, we were dealing with the scalar equations, which is nothing but the regular Navier-Stokes equation. With forcing, divergence free, and they are just supplemented by a quantity that we call theta, which is nothing but a passive quantity transported by the flow. Here, of course, we're still on the torus, and theta of x is in R. Basically, it's a scalar. And it represents a temperature or small variations of a temperature field. And this we coined the ns theta equation. And perhaps the fundamental remark was that although the addition of this line seems pretty much innocuous, and that although the basic properties of the Navier-Stokes and of the Euler seems to be unchanged by by the addition of this guy, in particular it's relating to symmetries and conservation laws. Well, when we let we have nu here, but the scalar can be subject to diffusion and to a source. So the conclusion was that, okay, if you put nu, f, kappa, and g go to 0, everything seems to be pretty much under control in the sense that in this limit, the symmetries of the original Euler are preserved. And there is just one additional symmetry, which comes from the linearity of the scalar. So to summarize, in the invisible limit, symmetries of the Euler are preserved. The only difference is an additional degree of freedom for the scaling symmetry, but there exists none. And essentially, this degree of freedom is just you change x, t, u, and theta by a factor lambda to the power lambda to x, lambda to the power 1 minus h t, lambda h u. But theta, you can change it the way you want. Let's put it lambda h prime theta, where here lambda is a positive number, and h and h prime are also real. Okay. And so the only difference is this additional degree of freedom here. But apart from that, Okay, the symmetries are pretty much alike. That's a fundamental remark. Yet, when we control the forcing of the velocity field and of the scalar, and we let nu and kappa go to 0, the statistics look very different. Statistics of theta are very different from the statistics and so in particular the scale invariance is broken. Scale invariance is broken, but so this is like in for the velocity field, but it's more broken in a sense than for the Navier-Stokes. Then this can be quantified by the fact that we observe numerically that apparently the exponent related to the structure function of the scalar, so delta theta of p of L divided by log of L. Okay. So this apparently goes to something which is goes to a constant value, which we may write psi star, which is finite. And the consequence of this kind of behavior is that, this we argued from a theorem by Kolmogorov, that we expect the scalar to form shocks. So this implies that the scalar field is maximum of in terms of regularity. It has maximum zero-order exponent. Has zero-order regularity. So the question is basically, how does why is it so different? And can we at least explain it by some easy argument? That was so the question is, how does it connect? Does that connect to essentially the statistics of the NS theta? So before we will dive further into this difference, but I want to further comment on this point first, just by revisiting a small stochastic model that we have seen I think last week. So it was the random, what we call the random H model for the scalar. And I don't know if you, so to state it, rapidly, the random H model is just a small stochastic model where on each we have some index, which are integers, and on each index we are going to associate a stochastic variable, theta n. last time we had UN as well. And of course, there is a scale, which is lambda n is lambda. Ln is such that Ln is lambda minus n. And also we have a time, tau n, which is nothing that we define as Ln divided by un. Okay? And so we had argued that in this kind of representation, it was pretty easy to account for what we were seeing from the Navier-Stokes. And the idea was the following. The idea was the following, was to just to propose a stochastic dynamics. So propose a stochastic dynamics which essentially consisted in writing un is equal to lambda minus hn times u0. Sorry, times un minus 1. So the hns are also parameters here. Where the hns are drawn from a given distribution, we call H, identically and independent and between them. So with this, basically, we could write an expression for UNP average, which was nothing but lambda minus P H to the power n times U0P, which implies in particular that this is lambda to the power minus n of zeta p, provided that zeta p is minus log of lambda to the power minus ph. Okay. Easy. So since we have this initial degree of freedom here, so this h prime for the theta, which is very different, a priori is unrelated to the h of the u, we can play the same game for theta. We can also introduce another dynamics, similar, so something like theta n is equal to lambda minus h prime n theta n minus 1, okay, with h prime independent and I think identically distributed, so that we obtain in the end that the structure function associated to this variable, theta, order p, is the same formula, but this time with lambda minus p h prime. Okay. Now, of course, this is if those two were totally independent, if the h and h prime were totally independent, this would be perhaps not very interesting. But we discussed yesterday another relation, and this relation something that we call the Yerglom relation. Implied that in the inertial range, we expect that delta u, delta theta square suitably average is minus 4/3 of L. Okay, times input of energy. And so this suggests that if delta U scales as L to the power h, and delta theta scales as L to the power h prime, then Yaglom implies that we have a relation between h and h prime, which is nothing but h plus 2 h prime equal 1. Okay, so this is what we're going to do. And h prime is equal to 1 minus h over 2. Okay, so same business as the other day. So if h is something which is peaked at 1/3, for instance, then h prime is also peaked at 1/3. So the scaling are the same. The scaling of scaling. So sorry. So this implies that those two guys will coincide. Okay. On the other hand, if we take something a bit more sophisticated, we take H, which is say a normal with a certain distribution C1 and normal sigma 2. Okay, then we obtain we can obtain a relation for the psi p, and we obtain that psi p is something linear, but there is a small correction, p2 over 2 c2, with c2, I think it was sigma square over log of lambda. Okay, so that's what we see. And so clearly, using this relation, this suggests to take h prime also as a normal distribution, but since we are divided by 2, so this means that we're just shifting the average. It's n times 1 minus C1 over 2, and the variance will be just divided by 4. Okay, and so this gives us a new relation, which is zeta of theta p, which is p times 1 minus C1 over 2 minus P2 over 8. Okay, so in a sense, we have a model here. We have a prediction, which has the same quality as the prediction that we made the other day. We have a prediction that ties the structure function of the scalar given the structure function of the velocity field. And so the question, how are we happy? In general, we could be happy for many things, but for this particular question. And this we can we check. So we are just use this. We are just going to use this data and then see whether this works or not. And so this is the result. Let's put it here. Yes. So on this line, so you have many plots, perhaps too much. The dots here is what we discussed the other day. So the dots are the exponents for the velocity field. Here, 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 here. The crosses here are the data that here. This is a red line. Okay. Those are the dots. The green line is the Kolmogorov prediction. So this thing here, P/3 monofactorial scaling. And the blue line here is the fit with a good value of C1, which is basically. And in fact, here C2 is also tuned, so that basically the zeta of 3 is 1. There is in fact only one parameter. So with this value of C1, which fits perfectly, we compute this formula. And this formula is the red line. And so what is quite striking is that it doesn't work at all. We're really not happy. So this is the, let's say not quite, because, okay. We have a prediction, but it's not very good. And so this is because of this kind of deficiency that we can see that, in fact, we don't really understand. It's not clear, in fact, how the scalar ties to the statistics of the velocity field. And of course, here the choice that I made to take H prime as a normal distribution is pretty much arbitrary. But if I assume that those two are indeed distributions in the, conjugation, whatever, well, the prediction is very bad. So it suggests that in this kind of representation, we should not only change the parameters, but we should also probably change the shape of the distribution. So the connection between those two sets of data, the velocity and the scalar, seems to be quite hidden. And so to get insights on this kind of question, today, and that will be essentially the topic of those hour and a half, it is to talk about a stochastic representation of the scalar. And so maybe the title of this lecture will be, you can see, insights from stochastic representation. So, so what do I mean by stochastic representation? Well, we have seen an example of representation. So in a case where kappa equals 0, g equals 0, we have a deterministic representation. Which comes from the fact that the scalar only describes a quantity which is transported along a trajectory. So if this is xt, this is a trajectory which is at time s somewhere, and is passing through xt at a certain time t. Okay, yes?
Is this the case even if the underlying flow has viscosity?
This is exactly what we're going to discuss. So, well, so this is the case even if so this is true even if the underlying flow has viscosity. What is not clear is what will happen when the scalar has some diffusivity. Okay, and so basically here we have nu, which is the viscosity. Just basically, the only requirement is that the velocity field is sufficiently smooth. There is no singularity, no shocks, and so on. And so in that case, we have that theta of xt is nothing but the value of the scalar at anywhere, actually, along the trajectory, s of xt at time s, in particular at time 0. So it will be theta 0 of x0 xt. Okay. Deterministic representation, easy. And so what we want to do, basically, we want to add essentially kappa not equal to 0 and f g, sorry, g from 0. What becomes of this formula when we have those, the diffusivity which is not equal to 0? And so in that case, where kappa is not 0, the representation formula will involve average, well, in a suitable fashion, along what we may define as noisy trajectories. And so noisy trajectories. So what are the noisy trajectories? It will be simply a particle. It will be a stochastic process, xt, okay, such that x of t, knowing that I was at a certain position x0 t0, x0 0, let's put it. It's x0 plus the integral between 0 and t of u of x of s ds plus the term, the stochastic term, which will be kappa times a Brownian motion, omega t. So we have kappa here, so we have a small kappa here, and small kappa here. And of course, we have this guy, where omega t is essentially, that's another definition, a Brownian motion. Here in in 3D. Okay, so what is a Brownian motion? So here we are going to just define it in 1D because it would be easier. Essentially, Brownian motion is a stochastic process such that T, for each realization, we are continuous. Okay. Omega is Gaussian. And centered, such that, so this means that essentially the average of the Brownian motion is 0, and that the correlation function is the minimum of S and T. And we, to define it in a canonical way, we will require that at time 0, omega 0 is 0. Okay, that's the Brownian motion. And so this means that I can take, in particular, I will be able to take averages with respect to the Brownian motion. So averages with respect to Brownian motion. Those will be averages that essentially, if you have a path, I have a Brownian motion which is here. Up T1, Tn, T2. Then the average of any observable phi with respect to Brownian motion. It will be the integral of dx1 dxn times phi of x1 xn times the exponential of, so I never know how to write it, so we can write it in a suggestive way, which is g of x1 to 1, x0 times g of xn to n knowing xn minus 1, with g of x1 to x0 is nothing but one of is a Gaussian distribution 2 pi to exponential of minus delta x squared over 2 tau. Delta x is x1. Okay, so that's essentially what we mean by when we take an average with respect to a Brownian motion. So basically, we have this notion of Brownian motion. We have a notion of noisy trajectories. So what we will want to do is to usually to take averages with respect to this guy, and meaning that when we take averages with respect to this guy, we are going to average over those noisy trajectories. So in order to do that, a very convenient tool that which I will just scratch the surface is Ito calculus. So here I will just present some kind of Ito cheat sheet to basically in order to be able to compute some of those guys. And so this formula here of the noisy trajectories, in fact, can be. I will erase this. Fine. So this formula here means that formally we can write this process as a differential, and this differential is dx is equal to u of x t dt plus the a noise times an increment, small increment of my Brownian motion. So this is what it means with the requirement that start from T0, it's better. X of T0 is X0. Okay? And in particular, to take averages with respect to this guy, we will need to use the celebrated Ito lemma. Which tells that essentially, so if I take y of t equal a certain functional of the of my trajectory for phi sufficiently smooth, has to be, in fact, at least L2 in the OT. NC2 as well. Then this process satisfy the stochastic, or rather, has the stochastic differential dy is dt phi plus u dot dx phi dt plus kappa dxx phi dt plus dx phi times square root of 2 kappa times d omega. Good. Well, here, meaning that yes. So meaning that essentially yt is phi of x0 t0 plus the integral between c0 and t of this guy here, ds phi plus u dx phi plus kappa dx x phi. Yes. Plus the integral between t0 and t of dx phi, which is taken, of course, at x of s times d omega s. So this we have an integral here. It's an integral. It's a stochastic integral. And this integral is defined in the Ito sense, meaning that we define well, the integral between, say, 0 and t of g of s d omega s, or g stable, is essentially non-anticipating, as the limit when n goes to infinity of the sum I equals 0 to n minus 1 of g si times omega of si plus 1 minus omega of si, and si is nothing but I times t over n. Okay. That's in the Ito sense. Ito integral. Okay, so for details about those kind of beasts, I can just tell you to look at any probability book, but probably a book by Oxendal is very good. There are some clean constructions of the volume motion and clean construction of those integrals. And so I think that what I want to tell you is essentially that the cheat sheet that we are going to use, that in order to compute any integral, we're just going to use the Ito calculus, which states that essentially some particle keys. Yes?
Why did you choose the noise to be a running motion?
Because I know how to define this. No, there are several reasons, but you will see. It will. There is a reason for it. And of course, there is a reason which you may hint already, that Brownian motion relates to when you average a Brownian motion, usually a diffusion term pops out. Okay, so since we want to deal with a case where we want to deal with the right-hand side where we have a Laplacian, then Brownian motion is probably a good idea to toy around. So this will be the mathematical reason behind it. Key to Ito calculus. Just use essentially d omega square equals dt. D omega dt equals 0. And d omega of 2 plus n equals 0 for n greater than 0. Meaning that essentially the integral of g times d omega of 2 plus n, 0 and t, equals 0. Integral n t, the d omega dt over g equals 0, and the integral of 0 and t of g times d omega square is the integral between 0 and t of g, ds. Okay, and those equalities have to be taken in the L2 sense. So I think that's about it for right now, and then we are going to use this after the break to represent the scalar. Break until 4. There will be it's a suspense.
The suspense, okay. After the break.
After the break, after the lecture.
After the commercial.
Yeah, exactly. Ah, this is serious. This is serious. Partially, it's
Yes, so if you ever do partial differential equations course in IMPA, this is the book
yeah.
using all parts.
Ah,
Tá falando?
já achava que estava mute. Agora é bom? Agora é aberto? Ah, bom. I realized that I forgot to tell you about one key property about those stochastic integrals that we will need. That basically, if you take the observation, we'll make two, basically. The fact that the integral between 0 and t g of s omega, when you take an average with respect to a point in motion, this is 0. And in particular, basically this means that essentially we can put the averages inside. So this means that essentially the 0, t, the averages break. This is equal to g of s, d omega of s, 0. Okay. And the second property, just an example also, an easy example before something that will be a bit more involved, I think. That if you take, so a noisy example, the easiest noisy trajectory is one for which the underlying velocity field is vanishing. So an easy case, an easy application of Ito's lemma. So take noisy trajectories. We take a noisy trajectory such that u equals 0 and kappa equal 1. Okay, so that dx equal simply d omega. Okay, so there is nothing, no advecting velocity. And then, for example, if we take take Ito's lemma with phi equal x2 over 2. Okay, then you will get d phi. So you have to differentiate this guy. It will be x d omega, and then differentiate this guy twice, plus 1/2 of dt. And so since x is omega, so we take an x of t equals 0 equal 0. So in particular, this means that this implies that d x2 over 2 is equal to x d omega plus 1/2 of dt. X is nothing but omega here, the Brownian motion. D omega square over 2 equal the Brownian motion times dw plus dt over 2. We integrate this with respect to time between 0 and t. And we get that this is omega square at time, w square at time t over 2 minus omega square at time 0 over 2. So this is 0. And this is the integral of 0 and t of w d omega. Omega times d omega plus t over 2. Okay, so basically with Ito's lemma, you can compute this integral here. So this implies that the integral between 0 and t of omega w times dw is nothing but omega square over 2 minus t over 2. Okay, and this so this is a okay. So this is an example of a computation. And as an exercise, you can retrieve this result by computing the limit n goes to infinity of the sum for I equals 0, n minus 1 of omega I times omega I plus 1 over n minus w I over n. That's an easy exercise. Just an example that basically is of the kind of averaging that we really need to do. So now that this has been stated, we can represent our scalar field. And so now, so we come back. So let theta u solution of the ns theta equation of the ns theta equation. Okay. Then consider, okay, we'll the case G equals 0 for now. Very simple, so no forcing on the scalar source. Then the scalar at a given position in time and a given position in space can be expressed in terms of the initial data at time x 0. Okay, so average over certain trajectories that we are going to call x tilde, which are trajectories which are the same thing. So we are, and this is time, this is x, this is 0. So this is where we want to look at. And from there, you have some noisy trajectories that go here, come here. You have some, okay, simply averaged over the noise. So what it means is that you have your initial data, you have different values of x1, x2, x3, and then basically, if you condition those trajectories to end on xt, then you can express the scalar as an average over the backward trajectories, with an average which is to be taken with respect to the noise. In other words, if we want to write it formally, we can write in the following way, which is the integral of, with respect to say the position in space of delta of y minus x kappa of 0 xt averaged times theta of 0 of y. Yes. And this is, and this also be written as theta of xt, which is the integral over dy. So this is something that can be interpreted as a probability. The probability of a given particle, which is at a certain position xt, which is the required position at time t position x, be at position y at time 0 times theta 0 of y. Okay. And so this is exactly the definition of this guy. So it's delta of y minus x 0 xt there is something a bit weird in this formula, is the fact that we are going backward in time. This is a bit weird. We have x is here, x is here. Okay, and we have some those trajectories which are basically trajectories conditioned on their final position. It's a bit weird. So we need to give a precise sense to this. So I just want to give you a flavor of the way we can prove this kind of formula. And the key is basically simply Ito calculus. So for that, consider, let us define the reversed in time velocity field that we are going to call U tilde of x S tilde is equal to U times x time position t minus S tilde. Okay? For this we can think of the okay, and similarly, theta tilde of x S tilde is equal to theta of x t minus S tilde. And because I took, so for theta it don't change, but for the velocity field, because I'm taking there's a minus sign here, so I will put a minus here. Okay. And then I will so observation. So we remember that we had d theta plus u d theta equal the Laplacian applied to theta plus the source. We said we are forgetting the source. We don't like the source. And so if I take u to minus u, this implies that the scalar field theta tilde is going to satisfy a new equation. Satisfies, and basically this equation is obtained by putting a minus sign here and a minus sign here due to the u tilde, and keeping this one with a plus sign. Satisfies minus d of S tilde of theta tilde plus minus u tilde dx of theta tilde equal this guy. This is the key part, in fact. So we can put everyone. We can put everyone on the same side, so that we get, in fact, this S. A plus sign is here. Okay. So this is what we want. In fact, this is really the reason why we are doing that. We get this plus sign here. And so now consider now a noisy trajectory for the reverse field. The reverse field. Something like a particle satisfying d of x tilde is u tilde of x tilde t dt plus a noise. So I call S. And with the initial condition that x tilde at t tilde equals 0 is x. So basically, the idea is that I'm going to start from here, but instead of going this way, I'm going this way. That's it. And so now we can apply Ito lemma for the reverse field, for the reverse for the tilted scalar on at different position prescribed by x tilde. Now, let us now apply Ito's lemma to the process y of S tilde is equal to theta tilde times x tilde S tilde S tilde. Okay, so when you do that, you obtain that dy is the derivative of dx tilde of theta tilde times the field over there times u tilde x tilde S tilde to the square root of d omega S tilde plus, of course, 1/2 of the gradient x tilde theta tilde times kappa ds tilde. Okay, and plus, I have to derive with respect to S tilde, ds tilde of theta tilde, ds tilde. Okay. And so now we look at those pieces, and we see that we have this piece, and this piece, which, by the virtue of this equation, is exactly 0. So this cancels. And so in the end, we are left with the square root of 2 times kappa times d omega of S tilde. We now take the average. And we get 0. There's a kind of, it looks like some kind of black magic here. But this is really what happens. And so what we need to do is to understand what is this guy. at the instant s tilde equals 0 and at the instant s tilde equals t. We integrate this guy, so this means that between 0 and t. This maybe we are going to keep. So now we integrate this guy between s tilde equal 0 and s tilde equal t. And so we have the result that the reverse field for reason s tilde of s tilde equal t, s tilde equal t is equal to theta tilde of x tilde s tilde of 0 s tilde equals 0. Okay. And so we have to. So what's happening at s tilde equal t? For s tilde equal t, s tilde equal t implies that s, the original time, is 0. S equals 0. Okay. So this piece here is nothing but this s tilde. So this is the value of theta at time t equals 0. This is nothing but theta 0 for the reverse position. So this is this we obtain theta 0 of x tilde of s equals 0. X equals 0, knowing that I was time x at time s equals t. Okay. And this, on the other hand, for s tilde equals 0 and s equals t, then s tilde equals 0, s equals t. But I know that I started my definition at t equals 0 at x. This is nothing but the average of theta tilde, but this is theta tilde is theta, because of this, of x t. And there is no average to be taken because this is the initial position. This is theta of x t. Okay, and the shorthand notation that is useful using the shorthand x0 xt is equal to x tilde at position s equals 0 x s equals t. We obtain exactly the result that was announced. That is to say that theta of xt is the value of the scalar at time 0 averaged over the trajectories which wind up at position x at time t. And so the picture to have is really the one that was plotted before. Is the fact that theta at xt, you may have, because of the noise, different trajectories may wind up here, okay? And this is perfectly fine. What's happening here is that the value of the scalar at this point is basically the average of all those values. And so we understand here what the diffusion term is doing. The diffusion term is smoothing some basically initial value of the scalar that could be very, very, that could fluctuate a lot. The role of the gradient is to assure that everything is smooth at this point. And so here, smoothing really equals averaging over those trajectories. It is useful to make to ask what happens when we put forcing. And so this will be a bit less painful because we are going to do it so without forcing. So we have done that. Now we are going to do this. Yes.
Does this have anything to do with a martingale approach?
Yes, exactly. It's exactly. It's a backward martingale.
Backward martingale.
Yes, and so this is exactly. It is so the scalar in this sense, at least without. So in this sense, it expresses what we call a scalar conservation law, and it is a martingale backward in time. For in this sense, and yes, yes.
Shouldn't there be like some kind of weight associated to each of the points over the initial line with regards to the average? For example, say the two extremes of the interval you've drawn there. Say that it's much more likely that if we left from the left extreme, we would reach xt than if we left from the right.
Yeah, so in those kind of so first I agree this kind of formula is mind-boggling, and the reason is that in fact we are conditioning. So in fact we are conditioning this average on trajectories which end here. So indeed, it's possible that if you start here, you are going to go. It's much more likely that you are going to go on the left side. Okay, but this formula tells you that in fact those trajectories which go on the left side and which do not touch this point are unimportant. What is important is that condition on the fact that I am here, I compute the average. So this is a yeah, it's a bit mind-boggling. So I will just re-express this formula in the formal way that now that we have a sense, we know what it means. So formally, this guy here, so this means that theta of x t is equal to the integral with respect to space of dy times theta 0 of y times this probability p1 of y0, knowing that I was at x and t. And I will put a small kappa here. I will drop the 1. I will put it here. So perhaps we can see what's happening when we formally what happens when we derive this guy again. So we can observe that dt of theta of xt is equal to the integral of dy theta 0 of y of dt times p kappa y0 of xt on the one hand. And this is also equal to minus u dx theta plus kappa dxx of theta. And this we can express it as a certain operator, L, which depends on x and t. And which applies to theta. Okay? So to theta, but theta we have a representation formula for it. So this is nothing but the integral of dy theta 0 of y. So in this representation formula, the only thing that depends on x and t is this probability. This means that this guy is going to apply to this guy times L of xt applied on p kappa of y0 xt. Okay, so that basically it means formally, because the initial data is here. Arbitrary, it depends on the so this implies that dt of p kappa y0 of xt is equal to L of xt applied to the same field. P of y0 of xt, and this is nothing but we have a kappa minus u grad, so with respect to x, plus kappa grad with respect to xx. Okay, so so basically this can be seen as a green function associated to the scalar. the salient feature is that is the order of the argument, basically. And so what do I want to tell? Okay, so now that we have this, basically we can easily find the formula when we're forcing. And so with forcing, so scalar with forcing plus diffusivity. It will tell you that the representation is theta of xt is equal to this guy here. So I take the first part, which is exactly the same, p of y0 xt. This is the same part, and I need to, this is an integral over space, and I need to include a second contribution. And this contribution will look like this one very much. It will be the integral over time between 0 and t of ds, integral over space, dy, times the forcing. So what will contribute is the probability to find a particle position y at time s, knowing at xt, times the forcing at time and position ys. This is the formula. To see why this is true, we just have to apply this operator. So this guy here solves the ns theta equation with forcing. And so yeah, okay, it's okay. And so just to see this, we are going to apply the L operator to this formula, and we are going to check that indeed dt of theta is equal to the first piece. So it's dy theta 0 of y times dt of p, y0 of xt. And this is nothing but what we've called L. So this is L of xt. So because L of xt does not depend on y, we can put it here. Okay. And the second term is this one. So I have to derive with respect to t. So I will get the integral of dy times p y t xt j yt plus I put the integral between 0 and t of ds dy time we have the same dt which applies to this guy. And again, we have L of xt which applies to this operator p ys xt gys. Again, this does not depend on s, nor on y, so we can take this out here. And so if we sum up, So then we get that dt of theta of xt is equal to the L operator, L, apply basically on those two pieces, which is exactly the definition, theta, plus this term here, okay, with the fact that the probability to be at y, knowing that y is also at x at the same time, this is a delta function. This is delta y minus x. So again, you get g of xt here. G of xt is exactly equal to minus u dx of theta plus kappa theta plus g. Magic, and this is what happens. Okay. So there are, I want to, what do we learn from this? Well, there are two consequences. It means that, in particular, the scalar heavily depends, the statistics of the scalar depends, scalar statistics depends on the Lagrangian transition probabilities P kappa of x t prime xt t prime. Okay, and products of those guys. And so, for example, I think an interesting example. Consider the case where we take as the initial value of the scalar just the identity function. So basically, theta 0 equal identity. Okay. Then, so the theta of xt equal the theta 0 apply, so theta 0 of x 0 xt equal to x 0 xt average over kappa is a scalar, solves the scalar equation without forcing, without g thing. Okay. And an interesting case, if we, so this is, we take the identity. So now, instead of looking at the initial position, I will, so I have position x0 here, theta of xt. So I'm averaging about this position. And I will consider the displacement with respect to, so if, yeah, okay. I'm going to define, I don't know how to do this, but delta of xt is equal to theta of xt minus x. So it represents, so now I know how to do this. I'm at x. Suppose that I have a bunch of trajectories which come here. The average is somewhere like here. Oof. This is the average. So what I'm plotting is delta here represents the separation between the position x and the average of the initial fluid particles. Okay, and so this guy also satisfies a scalar equation, but this time it's a forced scalar equation. Okay, so this one, delta of xt equal x0 xt kappa minus x solves the forced scalar equation. So indeed we have that with this thing we have dt theta plus u grad theta equal kappa theta. So theta is this guy here. Okay, so I'm just going to write theta is x plus delta. This is x plus delta. Okay, so then we get that dt of delta plus, so here we're going to pick up a term which is the contribution from delta. And then there is a contribution from x that I put on the other side is equal to minus u x plus this term. There is just x, doesn't pick up anything. And I get theta delta. Okay, and this is minus u x in the direction of x. Okay, so this can be seen as a force term, g of x and t, with g equal minus u. So this resembles this is exactly the situation of a scalar with gradient forcing. Okay, so typically, imagine that you have a plate. If instead of doing that, you were to have a plate, you have a gradient of temperature over a distance L. You have T1, T0. Okay. And then you are looking at the fluctuation of, you define T of xt is equal to a small fluctuation plus the gradient T1 minus T0 over L times x. So this satisfies the scalar equation of dt plus u dot t equal kappa t. This is the temperature. And this term here exactly the same as this one. And this implies that the fluctuation around the mean temperature is satisfies the first Scalar equation, kappa theta minus ux times ty, t1 minus t0 over L. This is exactly the same situation with t1 minus t0 equal 1 and L equal 1. Okay, so this situation where we look at the separation, the average separation between a position and the initial trajectories of the particle is a situation which exactly satisfies the scalar equation with gradient forcing. It's kind of mind-blowing, but just to show you that this is the case, I will just show you a picture. So remember, this is what a normal scalar looks like, with where we integrate directly the scalar equation with a given forcing on the right-hand side. And this picture here, so on the left is what I've just shown you. And on the right, this is a scalar which is reconstructed from this formula. So we have a bunch of trajectories in a fluid. And at each position of the space, we are representing the average value of those trajectories at time 0, say, minus the current position. And what is here is just an illustration. It shows you that basically the kind of patterns are really the same. So this shows you that we are really looking at the same equation. Well, we can zoom. It's wonderful. And so this is what it means. So we have this kind of picture illustrate that a scalar can be interpreted entirely in the Lagrangian framework. Now there is another interesting feature that we should discuss, and it relates to why this kind of representation formula is useful for the study of intermittency, and this we will discuss tomorrow. So tomorrow, why representation formula is useful for intermittency. Thank you for your attention.